Before I start, I just wanted to remind you of some important consequences, some important features of quantum physics that we talked about last week. So we discovered last week that light has both wave-like and particle-like properties, and in that sense, light is neither a wave or a particle. It's something different, something new, something unfamiliar that can exhibit sometimes wave-like, sometimes particle-like properties. We also learned last week that matter, say electrons, can exhibit both wave-like and particle-like properties, so that matter is also neither simply a wave or a particle. It's something else, unfamiliar, that can exhibit both particle-like and wave-like properties. So in one sense, that discovery is a discovery that the microscopic world of light and matter is really unfamiliar. Another discovery is that in the microscopic world, the description of light and the description of matter becomes synthesized or unified, in that we describe light and matter in a similar way, in the same way. There were a couple of important consequences of this discovery of the wave-like, particle-like properties of light and matter. One is that there is a limit to our theoretical knowledge of the physical world. In classical physics, there's no limit to your theoretical knowledge of the physical world. And a second one is that when you make measurements, you disturb, you alter the whatever you're making the measurement of. So making a measurement, making an observation actually alters, changes nature. That's not true in classical physics. We don't think of that way in classical physics. Okay, so today's content, I'm going to talk about the atom. The atom is kind of the crown jewel of quantum physics, and we're sort of going to build an atom, or we're going to look at models of atoms. And I'm going to start this topic here, just giving you a little bit of history on the development of different models of atoms, how our picture or how we visualized atoms developed over time. I'm then going to talk about an important discovery related to atoms. It's that atoms, for example, hydrogen, emit light, but they emit light of certain characteristic frequencies or wavelengths. We call them line spectra. So we're going to talk about the line spectra of hydrogen and other atoms. That'll be the second topic. And then finally, we're going to explain the line spectra of hydrogen and other atoms with a model of the atom that incorporates these new features of light and matter that we've been discussing, the wave-like, particle-like features of light and matter. So that's the plan. Okay, so this is I got a few slides here that are just sort of cartoons of different models of the atom from Newton, which is, 400 years ago, something like that, through to 100 years ago, and the birth of quantum mechanics. So Newton thought of atoms as kind of, obviously, very tiny, unbreakable, hard spheres. And so if you were to imagine some container of gas in Newton's model of atoms as tiny, unbreakable, hard spheres, that container of gas, and here it is here, contains lots of little atoms in red here, all moving frantically around at high speed in random motion. And so this is a sort of a picture of Newton's model of atoms. This model is actually quite successful in explaining things like the relationships between the volume of the gas, the pressure exerted by the gas, and the temperature of the gas. So it explains the relationship between volume, pressure, and temperature by thinking of the gas as made of, at the microscopic level, many, many, many little atoms that are hard and indestructible and unbreakable and are moving around in fast, random motion. The next two models of the atom that I've got two slides on, one's called the Thomson's plum pudding model, and the other one's called Rutherford's solar system model of the atom. These are models of the atom that came about as it was realized that the atom is made of electrically charged components. So what we might call an electrified atom. And in particular, that atoms are built out of electrons, a newly discovered particle, an electron, a negatively charged particle. Atoms are built out of, in part, out of electrons. So these are two models of atoms that involve electrically charged building blocks and involve specifically electrons as components of the atom. So this is a picture of the plum pudding model of the atom. So here's the atom, and the plum pudding model of the atom, maybe nowadays it would be, I don't know, raisins in here, not plums. But anyway, the idea is that these little plums here are the electrons, and they're tiny little charged, negatively charged particles, and they're embedded in this pudding or cake here, which is like a positively charged cushion in which they're sitting, or a positively charged pudding or cake in which they're sitting. And so this is a model of an atom that has charged building blocks. It's overall neutral, so it has negatively charged electrons in it, has a positively charged pudding or cake or cushion in which those electrons are sitting. It explains things like chemical bonding and chemical reactions as being electrical in their nature. So chemical reactions and chemical bonding are related to the interactions between the and the exchanges of the electrons between these plum pudding atoms. So it could explain those features. So it was a breakthrough. There was a rival to the plum pudding model, and it's this solar system model here. So in the solar system model, it's got the electrons. So here's the electrons orbiting like planets in a solar system. And at the center, like a sun, there's a core, and this is what we call the nucleus. And so the electrons orbit the nucleus like the planets, like Earth, orbit the sun. And so this is the solar system model of the atom. Again, important thing here is it's a rival electrified atom. It has electrically charged building blocks. So it has electrons again. They've been discovered, and we're building an atom out of those electrons. And again, there's a sort of hypothesized positive ingredient in the atom. This time it's not a soft cushion or pudding in which the electrons sit, but rather it's a dense positive core around which the electrons orbit. And so this is the model of solar system model of the atom. And again, this is an important model because it's an electrified atom, and it can explain chemical bonding, can explain chemical reactions in terms of the electrical interactions between atoms and molecules made of electrically charged components. So I would say if you were around at the early on in the 1900s, these were the two models that not everybody, but scientists would be talking about as sort of competing models for what the atom looks like. And so there's a famous experiment. Here's a sketch of it, or here's a cartoon of it, that actually distinguished between these two models, and it validated the solar system model, and it kind of refuted the plum pudding model. And this experiment is called the Rutherford experiment, and it's an experiment in which particles, they're called alpha particles. We don't need to worry too much about what alpha particles are, but they're another form of charged particles that come from radioactive materials or radioactive sources. So in this experiment, alpha particles from a radioactive source are formed into a beam of alpha particles. So the way you would do that is, here's your radioactive source, don't get near it, put a couple of sheets of lead in front of it here, make a little pinholes or small holes in the lead sheets, and you've got a collimated beam that emerges through the lead sheets over here on the upper right. And so we've got a beam of these positively charged alpha particles. And those particles were directed onto a target, which was typically a thin metallic foil. So it might have been a thin gold foil. You can roll gold and other metals, often very, very thin. So you can make very, very thin sheets of gold. And so that might be a target. And the experimenters basically surrounded that target with what's called scintillators in green here. These are slabs of scintillators, which actually have the property that if they are struck by one of these alpha particles, they make a little flash of light. So if you build this in the lab, switch off the lights, and start looking at these screens, you'll see this amazing thing of these little flashes of light as these alpha particles travel from the source through the lead collimators, strike the target, are deflected in some way by the target, and then hit these screens. And you can see the pattern of the scattering of the alpha particles from the target by seeing the pattern of the flashes of light on these screens. And they used to sit in the dark for hours and hours and hours, counting the numbers of flashes of light on the different screens to observe the distribution of the scattering from the target. So that's a famous experiment, and in a way we still do it today. Okay. So here's a couple of cartoons, one upstairs here and one downstairs here, that represent kind of our expectation of what would happen to the alpha particles striking the gold foil if the atom was like the plum pudding model of the atom, or the atom was kind of like the solar system model of the atom. And the difference between those two models of the atom is not the electrons. They both have electrons in them. But the difference is the hypothesized positive component, positively charged component of the atom. So in one case, the plum pudding model is this soft cloud, this soft cushion of positive charge. The other case, it's the solar system model, is this hard, dense, rock-like core of the atom. And that big difference between the hypothesized positive charge in the neutral atom causes a big difference in what you expect for the scattering of the positively charged alpha particles from the atom. So let's look at this sketch up here is kind of the prediction for the plum pudding model. And this sketch down here is the prediction for the solar system model. And if you want to visualize this, just imagine the alpha particles as like little bullets from a gun. And we're firing them at a plum pudding model atom, and we're firing them at a solar system model. If we fire them at the plum pudding model, they're passing through a cushion. And bullets passing through a cushion, well, the cushion is soft and cozy. The bullets are hard and fast. They basically just go straight through the cushion, maybe just deflected a tiny bit. On the other hand, if you fire your bullets at the solar system model of the atom, at the center of the solar system model of the atom is this hard, dense core, rock, stone. If the bullets happen to hit the stone, the core, the nucleus of the atom, that's so hard and so dense, those occasional bullets that hit that central core can be bounced off in all directions, even backwards. And so the two models predict something very different for the scattering of the alpha particles. For the plum pudding model, where you're striking a cushion, you just get small angle scattering. For the solar system model, where you've got this dense core at the center, you also occasionally get large angle scattering. And so these two models were like competing in this experiment. Do we see large angle scattering? Do we not see large angle scattering? We saw large angle scattering. And so that verified a kind of solar system model of the atom versus this plum pudding model of the atom. And that's where we ended up at the beginning of the 1900s. So that was the sort of history of atoms. Now I'm going to talk about the second topic, which is atomic line spectra. And this was sort of a new emerging discovery at the beginning of the 1900s. And then we're going to talk about the explanation of the atomic line structure. And this is the use of quantum physics to explain that structure, that nature of the atom. Okay, so let me tell you about line spectra. So at this point, plum puddings failed, solar system successful. So I remember Bunsen burners. I remember being in high school and the Bunsen burners in the chemistry lab. Robert Bunsen was not just famous for inventing the Bunsen burner, but like any high schooler, he, like I or everybody else, wants to put things in the flame of the Bunsen burner. And he put all sorts of different materials in the flame of the Bunsen burner, all sorts of metals, for example, in the flame of the Bunsen burner. And he discovered that heated elements emit light, like we would discover if he hadn't already discovered it. Heated elements emit light of different colors. Heated elements emit light of characteristic colors of the particular element. And so that was an important discovery. And here's just a few examples. These are regular kind of materials that you might burn. So this is a wood flame. This is gasoline. This is methane. This is butane, two gases here. And you see all these materials burn. They all oxidize. And what you're seeing is different colors in their flames. And this reflects the different molecules or atoms that are involved in the oxidation process. Now, I want to show you the light that is emitted by a few elements. So I'm going to set the mood. And we're going to look at the light from hydrogen. So that would be a classic example of the light emitted from an atom. So in this tube is hydrogen. You know, the age of this hydrogen in this tube is a historical hydrogen because almost the age of the universe. Hydrogen was produced shortly after the Big Bang. And so whenever you have hydrogen, you're looking at something that is like 13 billion years old. So this hydrogen in this little glass tube is 13 billion years old, and we're going to look at the light that it emits. So I'm going to stick it in here, and I'm going to switch this device on, and it will heat up the hydrogen, and we'll see the hydrogen glowing. And so this is a color that comes from hydrogen, and that light, that hydrogen light, is actually pictured up here. See, it's actually a blend of several colors of visible light. So it is a blend of red. There's red light over here at long wavelengths, so this line here. It's about 660 nanometers, but it also involves shorter wavelength light, for example, the violet and the blue here that are near the 400 nanometers, so much shorter wavelengths. So we see just a single sort of color here, but it's really a blend of several different colors in the visible region that the hydrogen is emitted. If I show you another case, ow, that was pretty hot, actually. That's why I was given this thing to pick it up with. Okay, this is neon. Neon's not as old as hydrogen. Okay, neon was produced in stars, though. So this neon is also pretty historic. This neon in this tube was produced when some star exploded in a supernova, and in that explosion, the neon was spread out into the galaxy, and I've got some of it. So this is old too, but not as old as hydrogen. And so this is the spectrum of neon. It's really kind of beautiful, I think. And you're seeing a very different color here. You're seeing a lot more red and orange and yellow in this case. And what you're seeing is this spectrum here. So now we've got a much more complicated spectrum for neon. We've got lots of reds and oranges and yellows. There are also some greens and blues up here. So that's why that's so ow, that is still hot. Must learn to use this thing. Okay, got one more, mercury. Okay, I won't tell you this, bore you with the story of how mercury is produced. But anyway, here's the mercury tube. I'm going to heat that up. We're going to look at its light, and it's another kind of attractive color, I think. It's way down in the sort of shorter wavelength region, much more blues and violets and greens here. And what we're seeing predominantly is these colors in the mercury spectrum. So there's violets, there's blues, there's greens, and so forth. Also some yellows and so forth. I still forgot to use the thing to pick it up. Gosh. Okay. Anyway, we looked at some pretty colors of hydrogen, neon, and mercury. We just saw a blend of the colors, but up here I'm showing you that they're actually built of, they're constructed from very specific wavelengths, very specific frequencies of light that are characteristic of the atom, that are characteristic of the hydrogen or the neon or the mercury. And so hydrogen, neon, mercury, all atoms have a kind of fingerprint, have a signature. And, you know, if you're scientists, this is really interesting. How come? How come do they all have these characteristic patterns of light, line spectra that they emit? Can I understand? Could I possibly understand the hydrogen line spectra? Well, we're going to do that. Okay. But first, let me go on with the line spectra themselves. So it was realized when scientists started looking at the line spectra, it it was realized that the hydrogen line spectra, that was the simplest one that we looked at. The hydrogen line spectra have a very interesting pattern of frequencies and wavelengths or colors. So here's an example of that. So when we looked at hydrogen, we saw a blend of 4 different colors in the visible region of light. So we mentioned that there's a red color. We mentioned that there's violet and blue and a sort of green color. So the light that we saw from the hydrogen lamp is a blend of these 4 colors that are in the visible region. It turns out that those 4 colors are actually 4 members of a series of colors or lines that also include ultraviolet light that have a pattern for their wavelengths or have a pattern for their frequencies that obeys this little equation here. So this set of lines, there's 4 visible lines and there's more ultraviolet lines. They're called the Balmer series, after the scientists, I presume, that found them. They obey, their wavelengths and also their frequencies obey a very simple pattern. And it's a very simple pattern that's expressed by this little formula here. So the pattern is that the inverse of the wavelength is equal to a constant. It's called the Rydberg constant. We'll come back to that later. Times this stuff in parentheses. And this stuff in parentheses is really just a series of numbers, a simple series of numbers. So what's multiplying the Rydberg constant to get the wavelength is, in parentheses, it's 1 over 2 squared, which is a quarter, minus 1 over n squared, where n is an integer, and that n, the integer, is bigger than 2. So it counts 3, 4, 5, 6, and so on and so forth. And so whenever you plug in an n, like if we plugged in an n being 3, we would get a particular wavelength. If we plugged in n equals 4, we get a different wavelength. n equals 5, we get a different wavelength, and so on and so forth. And so it predicts a whole series, a whole family, a Balmer family of wavelengths. And that's what we're seeing upstairs here, where I'm just looking at the visible region, or downstairs here, where I'm looking at the whole Balmer series. So the red line corresponds to n being equal to 3. So if you plug in the number 3 here, square it up, calculate a quarter minus a ninth, multiply it by the Rydberg constant, take the inverse of that, you get a wavelength, exactly this wavelength. The green line, that corresponds to n equals 4. So if you plug in n equals 4 here, so that means you've got in parentheses a quarter minus a 16th, multiply it by the Rydberg constant, take the inverse, you get a wavelength that exactly corresponds to this green light here. If you plug in n equals 5, same thing. You're going to get a quarter minus 1 over 25 times the Rydberg constant. Invert that, you're going to get a wavelength. It's exactly this wavelength here, and so on and so forth. So, you know, the Balmer series, which is an equation for the wavelengths of the light in that series, it's a characterization. It's an understanding of a pattern of the line spectrum, but it's not an explanation of it, right? There's no explanation. Why is it, you know, 1 over 2 squared minus 1 over n squared? We don't know why it is right now, but it's just a recognition that there is a simple pattern lying beneath the colors of the light, the wavelengths, the frequencies of the light. Turns out that there's actually other series that hydrogen emits. So there's only, if you look at the hydrogen lamp and you look at the visible spectra, there are just 4 lines that you see. Those 4 lines are a large part of the Balmer series. But if you were to look, if we had eyes, imagine having eyes that can see in the infrared, eyes that could see in the ultraviolet, we would see actually other series of light that's emitted by hydrogen. So let me just mention that. I'll do this on the device I can't remember the name of. There's another series that's called the Lyman series. So this is a sort of partner to the Bauman series. The equation for the wavelengths of the light in the Lyman series, it's a similar but not the same equation. It looks like this. So the inverse of the wavelength, again, is equal to the Rydberg constant times some factor in parentheses. And this time that factor, it's 1 over 1 squared. So obviously that's 1. It's 1 minus this 1 over n squared, where this time n starts from 2 rather than starting from 3. So it's a very similar equation. The only difference is actually for the Lyman series, we've got a 1 here in this first term in parentheses. For Balmer series, we got a we had a 2 here. And then the other difference is that n, the number on the right, that starts counting for integers greater than 1 rather than integers greater than 2. So this is the Lyman series. Just to give you an idea, if we took n equals 2, so that would be the first line in the Lyman series. If I wanted to calculate the wavelength, so 1 over lambda, I've got to multiply by the Rydberg constant. The Rydberg constant, we'll come back to it later, but its value is 1.097 times 10 to the 7 inverse meters. And then we're going to multiply this by this stuff in parentheses, which is going to be a 1 over 1 squared, minus 1 over 2 squared, which is a quarter. And if I multiply all that out, the inverse wavelength I got was 8.23. I got a drunk H there, I think, times 10 to the 6 inverse meters. And that corresponds to, if I calculate the wavelength, just take the inverse of that, I got a number that is 122 nanometers. So that's a much shorter wavelength than visible light. That's in the ultraviolet region of the spectrum. So that's why we didn't see the Lyman series. That's why Balmer series was found before the Lyman series, because Lyman series was hidden in the unobservable, the ultraviolet to our eyes. There's another series, Paschen series. It sounds like Netflix video, but it's actually Paschen, P-A-S-C-H-E-N. And that series is given by the following equation. Again, it's going to look very similar. Is given by this little equation here. So the inverse of the wavelength is equal to the Rydberg constant again, times a factor in parentheses again. This time that factor is not 1 over 2 squared minus 1 over n squared, or 1 over 1 squared minus 1 over n squared. It's 1 over 3 squared minus 1 over n squared, where n, again, is any number integer greater than 3, so it can be 4, 5, 6, and so on. If we were to calculate the first line in this series, so that would correspond to n equals 4, I would do the same sort of calculation, right? I take the Rydberg constant. It's about 10 to the 7 inverse meters. I'd multiply it by this quantity in parentheses involving integers. So it'd be 1/9 minus 1/16, whatever number that is. And I've already calculated this, of course, because I'm well prepared. It's 5.3 times 10 to the 5. Inverse meters. It's much smaller than the Lyman series number because these integers in the denominators are much bigger. And so we could calculate the wavelength that this corresponds to by just taking the inverse of that. I got 1875 nanometers. That's much longer than the wavelengths of visible light. So this is also a hidden line. It's hidden in the infrared region of the spectrum rather than the ultraviolet region of the spectrum. Okay. Don't know what I'm doing. These lines are in the notes. So here's the Lyman series. Here's the Paschen series. And here's a remark I wanted to make. So this Rydberg constant. So this is a constant that kind of sets the scale, the overall scale of the line spectra from the hydrogen atom, for example. If you were to, supposing, let's play God, let's change the Rydberg constant. If I could change the Rydberg constant, if I increase the Rydberg constant, I'd actually shrink down all the wavelengths, all the wavelengths corresponding to the light that's emitted by hydrogen. If I decrease the Rydberg constant, then I'd actually stretch out all the wavelengths. But I wouldn't change the patterns. The patterns would still be there. All those curious patterns like 1 minus 1 over 2 squared, 3 minus 1 over 3 squared minus 1 over 4 squared. All those patterns would still be there. And so that puzzle would always be there. What is the origin of that pattern? What is the source of that pattern? That was a huge question early on in the 1900s. And solar system model couldn't explain the pattern. There's no explanation for it in the solar system model. Plum pudding model couldn't explain the pattern. These models failed to explain the pattern. Okay, so now let's move on to how the pattern was explained, how this great mystery detective story got resolved or solved. And it's resolved or solved through what we discovered last week, wave-particle duality of light and matter. And it's solved through building a model of the atom that incorporates the wave-particle duality of light and matter. And so this is why this understanding of the atom, for example, the hydrogen atom, is kind of the crown jewel of our understanding that light and matter have particle-like and wave-like properties. Okay, so I just want to remind us of that. Remember that what we think of as particles in our everyday world, in the quantum world, particles have a kind of fuzziness or diffuseness. That is that they exhibit wave-like properties like interference and diffraction. That is that they have an associated frequency and wavelength. And that light, what we think of as waves in our everyday world, at the quantum level has a sort of discreteness or granularity to it. It comes in packets. It's absorbed in packets. It's emitted in packets. And those packets have characteristic energies and momentum. So this is the wave-particle duality of light and matter. This is the synthesis of light and matter into a single, unfamiliar thing. I could give it a name, right? The name would be a quantum field. But it's just a thing we don't have any experience of in our everyday in our everyday world. And so we just have to live with that. We don't get to see this thing in our everyday world. All the time, from our everyday world, we want to think of something as a particle, think of something as a wave, but it's really not right at the level of atoms and molecules and subatomic things. Okay, so this is the originator of the wave-particle model of the atom. It's called the Bohr model of the atom, after Niels Bohr. And this was the model of the atom that actually explained the line emission and absorption spectra that we've just been discussing. You know, those colors, those wavelengths, those frequencies of light from the hydrogen atom. So in this model of the atom, it sort of builds on the Rutherford model of the atom, but it adds in a wave-particle component to the model of the atom. So this slide and the next slide are the particle-like and the wave-like ingredients in Bohr's wave-particle model of the atom. So that's these next two slides are just how he built his atom. Then we're going to explore the consequences of the wave-particle model of the atom. And by exploring the consequences, we'll be able to explain the line spectra that's emitted by hydrogen atoms. So this is a slide that describes the particle-like aspects of the Bohr atom, and the next slide will describe the wave-like pattern of the Bohr atom. So from the particle perspective of the Bohr atom, it looks like a solar system model of an atom. So the hydrogen atom specifically is a single electron, here she is, orbiting a single positively charged nucleus, actually a proton. Here he is. So that electron orbits that proton, and in this solar system model, the attractive electrical force between the electron and the proton, these opposite charges, is providing a centripetal force. So there's an electrical attraction here that provides a centripetal force, kind of like for the planets. There's a gravitational attraction to the sun that supplies a centripetal force. And we can describe that by an equation. I filled in the expression for the electrical force between two charges. Their sizes are E, so that electrical force is Ke squared over R squared. I filled in, I remembered back to when I took 211 50 years ago, 60 years ago, and the centripetal force is mv squared over r. So I filled that into. And this is a little relationship that's predicted by the solar system or the particle-like model of a hydrogen atom. It's a relationship between the speed that the electrons orbit with, so that's the v, and the radius the electrons orbit with. So it connects the two. Think of it as exactly this. It's a relationship between v and r, speed and radius of a orbit, of an electron in an orbit. And so that's one ingredient in the atom. And then the other ingredient is on this slide. This is the wave-like ingredient of the atom. So this one's a little weirder because we think of electrons as particles, but it's only weird because we think electrons are particles. Electrons don't think they're particles. They're not particles. They also have wave-like properties. So this one builds on the wave-like properties of an electron. So an electron in this picture is a wave. So in the atom, it looks like a wave. And here you see in blue the wave, right? This is the electron wave around the nucleus. You see it at one moment in time when, say, it's a crest at this location up here. Another moment in time where the wave has changed to a trough at that location here. So this is a wave of electron matter wave in the hydrogen atom. And Bohr's idea was that the only waves that are allowed in the hydrogen atom are ones that kind of perfectly fit in the hydrogen atom box. That is, that the circumference of the orbit corresponds to a whole number of wavelengths. So this restricts you to what electron waves can fit in the box. You could have the circumference of the orbit being equal to 1 wavelength around the whole orbit. It could be equal to 2 wavelengths around the whole orbit. It could be equal to 3 wavelengths or 4 wavelengths around the whole orbit. It has to be a whole number of wavelengths. If it wasn't a whole number of wavelengths, then you could imagine that the wave would kind of interfere with itself when it came back round again. It would interfere destructively with itself, and it would cancel itself out. So the only stable wavelengths are where there are whole numbers of wavelengths, so the wave, it becomes a kind of standing wave, like on a violin string or a guitar string, that is stable in the hydrogen atom. So these are the allowed waves in the hydrogen atom. This idea actually leads to a second relationship between the speed of an electron in the hydrogen atom and the radius of the orbit of the electron in the hydrogen atom. That second relationship comes from this idea here. So 2 pi r is the circumference of the electron's orbit. So that's the 2 pi r. It's nothing other than the circumference of a circle. And lambda is the wavelength, the corresponding wavelength of the electron. N lambda, n is an integer, times the wavelength, is the number of wavelengths that fit around the circumference. So this idea leads to this equation describing the wave properties of the hydrogen atom. And this equation that the circumference of the orbit is a whole number of wavelengths is a second equation relating r and v, the speed. Because the wavelength, the de Broglie wavelength, is related to the momentum. It's Planck's constant over the momentum. Momentum is related to the speed. It's mass times speed, mass times velocity. And so this, it's not directly shown here, but this is a second relationship between radius and speed of the electron in its orbit. So now you've got 2 relationships between R and V. The particle-like solar system relationship, and you've got the wave-like standing wave in a box relationship between V and R. So to solve the problem of the hydrogen atom, all you need to do at that point is remember that 2 equations, 2 unknowns, you can solve for the allowed radii, the allowed speed of the atoms, of the electrons in the hydrogen atom. And so that's all they did. There's just a little bit of algebra, but to put those 2 equations together, they're describing the particle-like properties, the wave-like properties of the electron in the hydrogen atom, and you get predictions for R and V, the radius of the orbit, the speed of the orbit. You actually get a prediction for all the different values of n. So if you've got if 1 wavelength exactly fit in the orbit, so n is 1, then you predict a certain radius of the orbit and speed of the orbit that's associated with n equals 1. If you've got 2 wavelengths that exactly fit in the atomic box, the electron exactly fits in the atomic box, then n is 2, and then that predicts another pair of values of r and v, the radius of the orbit, the speed of this orbit that corresponds to n equals 2, and so on and so forth. So right, if you have n equals 3 waves in the box, you'll get another radius and another speed. 4 waves in a box, n equals 4, you get another radius and another speed. So you'll see that I'll be hanging subscripts on the r. I can hang subscripts on the v that label whether this is 1 wave in a box, one wavelength in a box, 2 wavelengths in a box, 3 wavelengths in a box, so on and so forth. And so this is Bohr's model of the hydrogen atom, the wave particle model of the hydrogen atom. There's not in some sense, there's not much mathematical in it, but there is something very new in it, that electrons have wave particle properties. So it has a bunch of predictions. So firstly, let me just stress again, by combining the particle light properties in this picture here, which relate R and V, and the wave-light properties, this is this picture here, which also relate the radius and the speed of the electron. That dictates that only certain orbits of a certain radius and of a certain speed are allowed. So there's an R1, V1 when you've got one complete wavelength in the box. There's a R2, V2 when you've got two complete wavelengths in the box, and so on and so forth. This is three wavelengths in a box here. So this picture here is n equals 3, this R3 and V3. If you know the radius of the orbit, that determines the electrical potential energy, because that just depends on the separation between the electron and the proton. So knowing R determines the electrical potential energy. If you know the speed of the electron in the atom, so that's the V, then you know the kinetic energy, because speed of the electron is going to determine its kinetic energy. So if you know R and V, you actually know the total energy, because you know the kinetic energy and the binding energy, which added together will be the total energy of the atom. That total energy of the atom, we call it, of the electron in the atom, we call its binding energy. It comes out to be negative because the potential energy is more negative than the kinetic energy, which is positive. And it's negative because it would cost you energy to remove that electron from the atom. So the binding energy you can calculate by just adding up the potential energy and the kinetic energies, which in turn are determined by the radius of the orbits and the speed of the electrons. So you can determine the allowed binding energies, which also can only take special values. There's a binding energy for one wave in a box, binding energy for two waves in a box, binding energy for three waves in a box, and so on and so forth. There's actually another feature, interesting feature of the wave particle model for the hydrogen atom, that not only does the energy, so the binding energy, just have allowed values, but also the angular momentum associated with the orbiting electron. That only has certain allowed values here. You can see it here. This is an equation for angular momentum from Physics 211. It's mass times speed times the radius of the orbit. If the speed and the radius of the orbit can only take certain values, the angular momentum also only takes certain values. Okay. So this slide tries to summarize those conclusions or consequences for only allowed radii or only allowed speeds, the consequences for the binding energies and the angular momentum of a hydrogen atom. So this is an important equation here. This is the equation for the binding energy of the hydrogen atom. E subscript n equals minus 13.6 eV divided by n squared. So the n here is, again, it's a label for the orbit, whether one wavelength, two wavelengths, three wavelengths fit in the hydrogen atom box. So this is E1, E2, E3, E4. The energy is written in units of electron volts rather than joules, much more convenient. That energy is negative because the negative potential energy outweighs the positive kinetic energy. And that energy is simply minus 13.6 divided by the square of n, the square of the number of waves that fit in the box. So the binding energy is most negative if you've just got one wavelength around the atomic box. It's less negative if you've got two wavelengths. It's even less negative if you've got three wavelengths. And there's a characteristic pattern for the binding energies in terms of n. So that's the binding energies of the hydrogen atom, this simple equation here. And as I mentioned, there's also the fact that the angular momentum of the electron orbiting the proton also only has certain allowed momenta. That equation is also rather simple. It's this equation here. L is the orbital angular momentum of the electron. N is this label we hang on it to indicate whether there was 1 wave, 2 wave, 3 wave, 4 wave that fit in the box. And then over here is the equation for the angular momentum. Look, it's just N times a constant, which is Planck's constant, divided by 2 pi. Just comes out to be this little expression here. So, if you've got 1 wave in a box, you've got an angular momentum that's just Planck's constant divided by 2 pi. If there's 2 wavelengths that fit in the box, you've got actually 2 Planck's constants divided by 2 pi, so it's just h over pi. If you've got 3 wavelengths that fit around the box, so that's this picture here, then the orbital angular momentum is actually 3/2 of Planck's constant over pi. And so that's the pattern. The lowest energy state of the hydrogen atom is what we call the ground state. That's the most bound one. It has the smallest orbital angular momentum. So that's n equals 1. The next highest state is what we call the first excited state of the hydrogen atom. So that's the n equals 2 state. It's the one that comes immediately, allows state immediately above the ground state. So that's the next most bound state. The next state after that is called the second excited state of the hydrogen atom. That's the n equals 3 state. And that's the next one in this staircase of allowed binding energies, allowed orbits, allowed angular momenta. And so it's the next most bound state after the ground state and the first excited state, and so on and so forth. That's just terminology. That's just language we use for convenience. I will stress this remark about the energies. So again, that binding energy is negative. To remove the electron, you're going to have to add energy to pull it out. So the binding energy itself is a negative quantity. For the ground state, it's minus 13.6 electron volts. I'd have to add 13.6 electron volts of energy to pull that electron out of the hydrogen atom. That negative binding energy is the sum of 2 concrete forms of energy: electrical potential energy and kinetic energy. The electrical potential energy is negative because you've got opposite charges, so their mutual electrical potential energy is going to be negative. That kinetic energy is positive. It's always positive because it goes as v squared. It turns out, I'm not explaining this at all, but it is interesting. It's true of the atom here. It's also true of the solar system, that the potential energy has twice the size. It has twice the size of the kinetic energy, and it has the opposite sign of the kinetic energy. So actually, if you take the hydrogen atom ground state, so that's a binding energy of minus 13.6 electron volts. The potential energy, the electrical potential energy, is minus 27.2 electron volts. That's twice 13.6. So the potential energy is a whopping negative minus 27 electron volts. The kinetic energy is actually half that and the other sign. So it's positive 13.6 electron volts. So that's the kinetic energy. So when you add the minus 27.2 electron volts of potential energy and the positive 13.6 electron volts of kinetic energy, you get back to that binding energy that's minus 13.6 electron volts. So that's the kind of, that's the accounting. I've become an accountant for the hydrogen atom. I've accounted the electrical potential energy, the kinetic energy, the electron, and the binding energy. That's how you account for it all. Okay. Here's a quiz question. Which just asks you to compare the binding energy of the first excited state of the hydrogen atom with the binding energy at the ground state. And so is that first excited state, is the ground state 2 times the binding energy of the first excited state, 4 times the binding energy of the first excited state, or 8 times the binding energy of the first excited state? So I'll just give you another minute or so to ponder, think about it. Yes? No. The remarkable thing is I got this far through the semester without that happening. But yeah, I didn't publish the quiz. Okay, so maybe I'll press on. The binding energy of the hydrogen atom, remember, is minus 13.6 electron volts divided by the square of n. We call that number the principal quantum number. It's the number of waves that fit, of the electron waves that fit in the atomic box. So the ground state is n equals 1, and the first excited state is n equals 2. So the ground state is minus 13.6 electron volt binding energy because we're dividing by 1. The first excited state is minus 13.6 electron volts divided by 2 squared. So that's 4. It's 13.6 divided by 4. I was going to do that in my head, but I'm standing up here. It's minus 3.4 electron volts. It's 4 times smaller than the ground state binding energy because the denominator in the equation, the n squared, is 4 times bigger than for the ground state. So that's the answer. Well, we started with the problem or the puzzle of the line spectra. We just built a model of the hydrogen atom, and I claimed it's going to explain the line spectra, and here's the explanation. So this is an energy level diagram. So in this energy level diagram here, horizontal lines, so for example, downstairs here, or this ladder of horizontal lines upstairs here, those are the allowed orbits. Those represent the allowed orbits. And specifically, the way I've sketched this is that the locations of the line are in proportion to the binding energy of each orbit. So over here on the right, each horizontal line, each orbit is labeled with its binding energy based on that equation, minus 13.6 divided by n squared. And over here on the left-hand side, these are the values of the n's, the number of waves that fit in the box. So the ground state is down here. It's 1 wavelength around the atomic box, and its binding energy is minus 13.6 electron volts. The first excited state, that's n equals 2, 2 waves around the box, and its binding energy is a quarter of this guy's, minus 3.40 electron volts. and so on and so forth. This is 3 waves around the box. The picture that I kept showing earlier was 3 waves around the box. It's this state here. It's bound by minus 1.51 electron volts. That's 13.6 divided by 9. And so on and so forth. Higher and higher n numbers. Higher and higher numbers of waves around the box. Lower and lower binding energies. More and more angular momentum. All that's shown in this plot. In addition to showing you the binding energies, I'm showing you the origin, the nature, the explanation of the Bauman series. That's the one that produced invisible light. And then the Lyman series that's in the ultraviolet, the Paschen series that's in the red. So here's the Bauman series. And remember, the key to calculating the Bauman series was 1 over 2 squared minus 1 over n squared. The 2 is the n value of the final state of the hydrogen atom. The n that's higher, the 3, the 4, the 5, is the initial state of the hydrogen atom. This is explaining the Bauman series that is associated with light from hot hydrogen, from heated hydrogen, as coming from electrons being in some higher state of the hydrogen atom, some excited state of the hydrogen atom, and decaying to a lower state in the hydrogen atom. Specifically, for the Bauman series, they're decaying to the n equals 2 state, that's the first excited state, from some higher lying state. Might be the second excited state, third excited state, fourth excited state, so on and so forth. So, here's the red line. It's actually from n equals 3, 3 waves in the box, to n equals 2, 2 waves in the box. Here's the other colors of visible light, the green, the blue, the violet. They correspond to shorter wavelengths, and they correspond to photons with greater energies, greater frequencies. And so this is the origin of the Balmer series. This is how Niels Bohr explained the Balmer series. Similarly, remember the Lyman series? That one had the pattern is 1 over 1 squared minus 1 over n squared, where n's 2 or bigger. That's when you got transitions down to the ground state, the n equals 1 state. And so these are the first lines of the Bauman series, n equals 2 to n equals 1, n equals 3 to n equals 1, and so on and so forth. These are much shorter wavelength. These are much higher photon energies, much higher photon frequencies. This is ultraviolet. And then on the other side over here, this is the Paschen series. These are the ones that are associated with that equation, that factor in the equation for the wavelengths of the Paschen series lines. It went 1 over 3 squared minus 1 over n squared, where n is bigger than 3. The 3 is the second excited state of the hydrogen atom. So these correspond to decays from higher states to the second excited state of the hydrogen atom. And they're in the infrared. And so that was, again, this is like a good day at the office. Oh, I've just figured out the Bauman series, the Lyman series, and the Paschen series. I've explained where those patterns of light come from. It's from a wave-particle model of the hydrogen atom. So it's an amazing breakthrough in understanding. All these breakthroughs were happening between roughly 1900 and 1930. It was a time, as I say, I'm very, very resentful about it, except that I'd be dead if I was around then. I'm resentful about it because all these discoveries, relativity, wave-particle duality of light and matter, this crown jewel model of the hydrogen atom, they're all done with basic algebra. They're all done with just very basic algebra and some sort of vague knowledge of general physics. Not much more. And some crazy ideas, right? Crazy ideas like electrons can behave like waves and light can behave like particles. Okay. I just wanted to show you that here's the formula for the different series, the Lyman, the Balmer, the Paschen series. Here I've written it in terms of frequency rather than in terms of wavelength. But obviously, if you know the frequency, you can convert it to a wavelength. So here's the formula that emerges from Bohr's wave-particle model. And in this formula, NF, this is the final state, the Lyman series lines end in, or the Balmer series transitions end in, or the Paschen series transitions end in. That's the N final. And this is the initial state that they come from, the higher lying state. So this is the initial state for the red, the green, the blue, or the violet light, for example, in the Balmer series. Let me just end on this remark. One other great achievement of Bohr's model of the hydrogen atom, the one I'll end on, is that it also predicted that constant of nature called the Rydberg constant. So up until Bohr's wave-particle model of the hydrogen atom, that was just the number that was measured. And nobody knew where that number came from. It was like a special number in nature. Where does that number in nature come from? Here was an explanation of that number. So when you construct the Bohr model of the hydrogen atom, its wave ingredients, its particle-like ingredients, you get a prediction for the Rydberg constant. Here it is, R subscript A. It's this guy here. It looks horrible. Contains a lot of other constants. But it sort of makes sense why it contains them. It contains the mass of an electron that's in the hydrogen atom. It contains the charge of an electron. It's in the hydrogen atom. It contains the strength of the electric force. It could be the constant K, or it could be the constant epsilon naught, because it's electric force that holds the hydrogen atom together. It contains the Planck constant, because Planck's constant is the bridge between wave and particle properties of matter. And finally, it contains the speed of light, c. Speed of light, c, we're emitting light. We're emitting light, and we're explaining the line spectra. So that's